Cool. My name is Behrad Babaee. I'm a technology evangelist in Aerospike. Today we are going to talk a little bit about Moore's Law. So probably most of you already heard about Moore's Law. Mr. Gordon Moore, one of the founders of Intel, wrote this article in 1965 and predicted that in the years to come, the number of transistors that we get in every couple of years is going to double. It was basically translated up until 2002 to this, that the frequency of our CPUs was getting doubled every 2 years. This was a great thing for the software industry because it meant that without doing anything to our softwares, our applications were running twice faster. So this was a great time. But around 2002, 2003, the growth in the CPU frequencies stopped. So as you can see in this line, around 2003, the frequencies plateau and the frequencies are not going any higher anymore. But as you see on the green line, the number of transistors are still increasing. The CPU manufacturers were trying to add more cache into the CPUs, into the chips. They were trying to add, more complicated instruction set to the CPUs, and then eventually they start adding more cores to the CPUs. And of course, it caused some changes in the way that software developers had to write programs. In 2005, there was this article that was, I think it is still a very good article to read, that says that the free lunch is over. It basically says that because the frequency of our CPUs is are not getting faster, that free lunch that we used to get every 2 years is basically going away, and we need to think about different ways. And it says that we need to turn toward concurrency. We have to improve the concurrency of our applications to be able to use the hardware that is available in the market and the hardware that is going to come in that we are going to get in the years to come. So I think since 2005, in computing industry, it's a very, very long time. I think it's going to be quite an interesting thing to do, to look at what happened since 2005 and where are we, and what about the predictions that this article had. So to do that, I want to compare two chips that we had back in 2006 and the best chip that we can get today in 2022. So the number of cores that we could get, the top number of cores that we could get in 2006 was, you could get 4 cores. Now today in the best Intel CPU, you can get up to 56 cores. It's 14 times more. There's a 16 years difference. It's 2 years. We should have had 256 more cores. If you look at the frequency is doubled. Again, very far from 256 times. The amount of cache is around 10 times more. Again, not even close to 256. And then actually the number of transistors is again around 14 times more, right? So when you look at it that way, it looks like that the Moore's Law is either dead or at least it's dying, right? But I think that it's an unfair comparison, because if you look at computers in 1965 or perhaps even 2000, the most important part of the computer was the CPU. But since then, a lot of things have changed, right? We have many more components in a computer. So I think it is fair to look at the state of the whole computer, the server that we get, how many transistors we get in a whole server, not on just a single chip. So now if we start to look at the number of the transistors that we get on the servers, back in 2006, your motherboard could have 4 sockets. Basically, you could have 4 CPUs on the motherboard. So you could get up to 16 cores. In 2022, you can have 8 sockets on motherboard. So you can get 448 cores on a single machine. It's slightly better, 28 times, better than 14, but it's still not close to 256 that we were expecting. What about the amount of RAM? A top computer, a top server back in 2006 could have up to 64 gigabytes of RAM. That's increased to 24 terabytes. That's 384 times more RAM, right? So, you know, it's kind of even, you know, lackluster number of transistors in CPUs, but RAMs kind of cover that. So now it's up to the disk. Disk can say that are we getting more transistors or not? So back in 2006, you could have a few tens of terabytes of disk. Now you can have a few hundreds of terabytes of disk. So on the surface, it looks like that, yeah, it's just 10 times more. But you have to look at it in a different way. The disks in 2006, they're magnetic disks. They're spinning magnetic disks, which hardly had any transistors, right? And when I'm saying that, you know, SSD technology existed since 60s and 70s. I'm not saying that they didn't, you know, that technology didn't exist, but we were not using that technology that often, right? So these machines, these disks, hardly had any transistors. But now, most of the disks that we are using are SSD, solid-state drives. And for each terabyte of disk, you get trillions of transistors, right? So in a CPU, you had billions. In 1 terabyte of SSD drive, you get trillions of transistors. So the number of the transistors that we get in a computer is not doubled every year. It's possibly, I don't know, 10 times every year since 2006. You can actually think about it like this, that back in 2006, the number of transistors was in scarcity, and now we have a lot of transistors. We have an abundance of transistors in a single machine that we get. And this is an interesting thing, so we want to have a look at this and see, did it affect the way that we program? So for a server that was in the scarcity era, we had 16 cores, right? The number of cores were limited, so we had to basically share the core between several tasks, right, to make all of them go forward as fast as possible. This was a good idea, but it has some side effects, right? So every time that you context switch, you are losing a little bit of performance, right? It is fast, but you know, it's a little bit of overhead. Now that we have 448 cores, we don't necessarily need to do those many context switches anymore. We can leave a task to a core, basically the thread per core type programming, and leave the core with the task till it is done. So we reduce the number of the context switches in the middle of the time that we are working on a task. So what about the disks? So the spinning disk had lots of limitations. So when we were writing programs, we were trying to reduce the random access to these disks because they were not really good in random seeks on the disk, finding the location on the plate and reading the data. And they were horrible for concurrency. You were not able to read concurrent things from these disks. But now we have these SSD drives that provide you with reasonably good random access speed, and also they have a massive concurrency. You can read 400 different things at the same time from the disk. So a lot of things that we used to do back in the day, given the type of the hardware that we had, is kind of redundant. So what about the size of the RAM? This one is the most interesting one. So back in the day, the ratio of RAM to disk was 1 to 250. So basically for each megabyte of RAM, we used to get 250 megabytes of disk. Today, on a top computer, you can reduce that to 1 to 10. Basically for each megabyte of megabyte of RAM, you can get 10 megabytes of disk. So back in the day, RAM was 0.4% of the size of the disk. Now you can increase it up to 10%. So a lot of the things that we used to do to use this very, very scarce resource, right? You know, like moving the RAM to disk and bringing the disk back to RAM, to keep that RAM ready for the thing that we are doing, becomes kind of redundant, right? We don't need to do that anymore. So if you have a program that was written in the era of a scarcity, if you want it on today's hardware, it's going to be like this. For going from A to B, you are doing a lot of things that is basically a waste of time. So going back at this article also says something else which is very interesting. It predicts that they're going to be the biggest sea change in software development since object-oriented revolution. It's a big claim, and let's see if there was such a revolution. So I think that there was such a revolution. So this article is correct about saying that there was a massive revolution in the way that the software engineers build applications. But it says that it's a turn toward concurrency, and I disagree. We didn't turn towards the concurrency, at least in a way. So if you look at the way that we created software back in 2006, we had these multi-threaded monoliths, and but now today in the abundance era, we are using single or few-threaded microservices. The other difference is that we used to use structural programming languages that were multi-threaded. So if you look at this side, these are the 6 popular programming languages in 2006. Only JavaScript is a single-threaded programming language. And back in the day, 2006, JavaScript was only used for very, very simple front-end stuff. But today, 50% of the market is using single-threaded programming languages. So it's a little bit, counterintuitive that what happened, we have these massive machines that have a lot of resources, but instead of going toward concurrency, we switched to single-threaded and few-threaded applications. So basically what we started to do, what we understood was that multi-threading is difficult. Right? It doesn't matter how much we try to make it simple with functional programming, with task parallel library in .NET, with Java 8, it was still difficult, right? So we wanted to have a way to be able to do multi-threading, to use all of these resources, but we were not able to really program for that. So we decided to go the opposite way. Instead of doing concurrent inside a process, we said that, no, we are going to make concurrency outside of the process. So we are going to create these single or few-threaded microservices, and we are going to dedicate resources to them, right? So we wouldn't have that problem that we had with, context switching constantly, because it's a single-threaded application, so you don't do any context switches. And you have a lot of RAM, you can assign enough RAM to this tiny microservice that you have. And your disk, yeah, it is shared between lots of services, but we have good random access, so we don't have any problem to access to the disk from lots of different servers. Well, I'm not claiming that this is the reason that we switched to microservices. There are lots of other reasons for doing microservices. I'm just saying that microservices matches with this abundance of resources that we have available on a single machine. It works with that. But there are some type of applications that are not microserviceable, right, if that's a word. There are some sophisticated multi-threaded applications that are usually stateful, like databases, right? There are some attempts to create single-threaded databases, but I don't know, I haven't seen any of them here in this event. So I don't think that many of them are still real, but I don't know, at least the most famous databases in the market, all of them are multi-threaded applications. The thing is that if these applications were written for a scarcity, because of those differences that I explained, that they existed back in 2006, they are not able to use this much resources, because all of those context switches that they are supposed to do, all of those moving the RAM to disk, all of those things that they were programmed to do is not going to work on this much resources. So I don't know, just for an example, if you are a Java developer, just assume that you give 640 gigabytes of RAM to the heap of your Java virtual machine, right? Each pause for doing, I don't know, a sweep of the memory is going to take tens of seconds, right? It doesn't work like that. So you have to program in a different way. So we said that, okay, how we can solve that? We have all of these applications that are working really well. So how we can fix that? And well, this was the slide explaining that what was going on and if you have a lot of resources. But yeah, the way that we tried to resolve that was that we said that, okay, we are going to create these relatively large virtual instances with a lot of resources, and we are going to put them on these massive machines that we have, right? So we started to do something like this. But it is basically this, right? So we didn't have the scarcity problem on the underlying system, but we tried to reintroduce the scarcity into the infrastructure so these applications that are not efficient to work with these massive systems can still work. So the thing is that, yeah, it works, and you can kind of scale your application, right? So nothing stops you from scaling. But because of all of these, I don't know, not going straight from A to B, you are losing a bit of performance. So the question is that how much performance we are losing because of this. So I don't know if you could join my talk yesterday. I had a talk yesterday that I was discussing efficiency of software platforms. I discussed this, that by increasing the efficiency of your application, not only you can increase the speed and the throughput of your application, it also reduces the amount of resources that you need. And you know, resources have cost. So reducing the resources can reduce the cost as well. And then I showed you that I released a framework that you can measure the amount of emissions that your software platform produce. And I showed that the efficiency can also reduce the emissions of your software platform as well in a significant way. So the question was that, okay, so the company that I work for, Aerospike, built a software that is 5 times more efficient than similar databases in the market, right? We are 5 times faster. We can handle 5 times more throughput. We are using 5 times fewer resources. The cost is 5 times cheaper, and our emissions are 5 times less than the other technologies. So how we are doing that, right? I've been in the database market for a very long time. I know a lot of databases, right? And I know all of them are using similar data structures and similar algorithms, right? A B tree is a B tree, right? There's no way to make a B tree 10 times faster. There's no way to make a red-black tree running faster. This is an algorithm created in 1970, right? So how on earth Aerospike is 5 times faster? And the answer is that Aerospike is built for the abundance of resources in the market. If you have a database that was written back in 2006 to 2015, most probably it's not able to use the resources in the market correctly. And because of that, you are losing a lot of value. And to be very honest, it is not only Aerospike. There are a lot of new technologies coming to the market that are working correctly with the hardware of today, right? So a lot of the technologies that we assume they're modern in this sense that they were written in after year 2000, but there's a new generation of modern applications coming out that are more suitable for the abundance of hardware that we have. And using those, you can do all of these as well. So I think as decision makers, as developers, as people who are interested in technology, it is your responsibility to figure out what these applications are, because these applications work better with the hardware that we have today. And the thing is that this gap, this scarcity and abundance gap is increasing, right? So the amount of efficiency and the amount of speed and reduced costs that you can get from your hardware is become bigger and bigger, and you shouldn't really lose. So my final word is that somebody can write today that the free lunch is not over yet, because if you're using this new technology, your software become faster and become cheaper, and it will produce fewer emissions. Thank you very much.